Okay, so we just did induction on gnats. Let's look at lists. And, so if you look at the list type in Haskell, it looks something like this, right? You got the empty list, or it's a cons of an A with a list of A's. I don't know. That may look unfamiliar. What if I say um, that might look a little bit more what you think, although this means the same thing. We've got this infix operator, colon, which is cons, instead of having to write it out like a constructor like this. So the type of this thing is it's constant, and it is a list of things of type A for every A. That means you're using the same symbol for the empty list for every single. It's highly polymorphic for every possible type A. And then you have a similar kind of thing that you have the type of cons, which you already know this is A arrow list A arrow list A. So let's consider a few functions on here. Like we could do append, which is written in infix using. So I'll give the definition of append. So first we say, okay, the empty list appended onto some y's is just equal to y's. And if I have x const onto x's and I append that onto some y's, that's equal to x const onto x's plus y's. Now, this might look a little bit like add on the previous lecture. Remember, add of z k is equal to k, and add s of j k is equal to s of j k. This is almost the same definition. And in fact, and so in that lecture, we showed that raw j, which is an that, adding j to z is equal to j. So an analogy with this, we can have, so this was proved in the last. An analogy to this, we can show that, consider append. Empty list is a right identity for append, just like 0 is a right identity for add. Okay, so the theorem we want to prove is that for all X's, which are lists of things of type A, that X's plus the empty list is equal to, maybe I'll say equals here, is equal to X's. And we said equals here too. Now, it turns out if we just try to prove this straight on without having list induction, we're going to run into the same problem. So what do we do for list induction? Well, list has two constructors. So what is list? I'll just nab this and bring it down below. I mean, maybe I should write them both out. Okay, so first, before we prove this, let's consider like versus NAT induction. So NAT induction was that, okay, some property holds of the empty list, some property holds of Z, and that property, and if for all J, which is a NAT, key holds for J implies P holds for, capital P holds for S of J. If those two things hold, then that implies that for every natural number, P holds for K. Okay, control. All right. Okay. Now, how did we get this? Well, we looked at the data type, which was like that. And so there's two cases. We got to show it for Z and we got to show it for S of NAT. But to do that, we get to assume that it holds for a smaller NAT. And if we do that, we've shown for every NAT. Now you might say, okay, why does that work? And so here's my explanation, which I think you don't see in many books. It's extremely elementary, but suppose that I proved some property and you said, you know what? I don't believe you, except that you believed that I showed P of Z. And you believe that I showed this, which was assuming P holds for arbitrary J, I showed that it holds for P of S of J. So all these two things, you agree. You said, yes, you proved that. But you say, but I don't believe the property holds for some, S, some number, K is a big number, let's say. So how does this work? Assume it doesn't. But you did accept P of Z and P of J implies P of S of J. You did accept those proofs. And this is for all J. Okay, so you say, but I don't believe the property holds for P of S of S of S of K times for of Z. But I can show you using my tool things. I could say, okay, you accepted P. The first step is you accepted P of Z. That you agreed to already. Now, two, take this little thing here that you accepted the proof of for this and plug in Z for J. You say for every J, this property is true. So every J, which is a natural number, this property is true. So that means I can plug in and I can say, okay, but that means that P of Z implies P of S of Z. And you have to accept this because you accepted my proof of this and you accepted the proof of this. And now, if I know that P of Z is true and P of Z implies P of S of Z, then the third step is I know that P of S of Z is true. Now I can do the same thing again. I can say, okay, but that means that P of S of Z implies P of S of S of Z. And then I get 5 is, P of S of Z. And so what is it? It's like, I don't know, 2K plus 1. Something like that. I get P of S, K times applied to Z. And so you have to accept it. So this is why induction on the natural numbers works. But it's also the same thing, the same reason that induction on lists work. So let's remember the definition of the data type for lists. Well, I'll do it like this, even though it's a little bit harder to read, but it's the same idea. So here's the data type, and so we want to say if P holds for the empty list, and for every list X's, which is of type list A, and I mean, you can switch quantifiers around, and I'll write it like this: for every X of type A, and for every list X's of type list A, if P is true for X's, if I could show that implies that P is true for X to cons on to X's, those two things together give me that for every say Y's, which is a list A, the property holds for Y's. Okay, so there's the induction principle. So how do you use it? Again, to show this, there's two cases. one arose from the base case. You have to show base case is show P holds for the empty list. And two, the induction step is to show that to get to for an arbitrary x, which is something of type A, and arbitrary x's, which is something of type list A, assume the induction hypothesis, which is that, which is P of x's, and show P of x constant to x's is true. That's how you use this. So if we go back up and we look at the theorem that we want to prove, and so this is the same thing as before. I mean, we're showing two cases. We're showing that this is true, and then we're showing that this is true. And we're showing that this whole thing is true by first choosing an arbitrary x and then choosing an arbitrary list called x's, and then proving that if I assume P holds for x's, then it holds for the cons of x onto x's. So let's go back up to this right identity one. Here it is. So how can we prove it? Copy. Proof is by induction on x's, which is of type list A. Property of x's that we're proving is that P of x's is equal to, we're defining P of x's to be that x's plus plus empty equals x's. Base case, P of empty is equal to empty plus plus empty. And that's just equal to, and that just equals empty by definition of append. So I mean, maybe I should show the definition of append. Okay, here is the definition of append. Copy. Bring it down below. Copy. Okay, so I've replaced y's by the empty list, and I get y's, which is the empty list. So this is just true by the definition of append. Just like the zero case for add was almost identical. So the induction step is assume that P holds for x's, for some arbitrary x's. I'll say for arbitrary x of type A and arbitrary x's of type list A, assume, and this is our induction hypothesis, P of x's. And what is P of x's equal to? P of x's is that x's plus the empty list is equal to equals x's. Okay, and we have to show P of x cons onto x's, which is equal to that x cons onto x's plus empty equals x cons onto x's. Now, a reason that I really like to write down, oh, and this is an equals, the property is because you can check yourself more easy. Sometimes you might do the property in your head, and it wouldn't be uncommon, at least for me when I'm doing this, to say, oh, and that's equal to x's, and it's not true. You need to substitute this x colon x's for all the x's here. It might have been a little easier if I'd chosen y and y's to see it, but I can choose x and x's. So this is what we have to show. Okay, so we've assumed it. So starting on the left, on the left side of the equality, x colon x's, plus empty is equal to x constant to x's plus empty. Now, by our induction hypothesis, up here, so this is by definition of plus, and then by the induction hypothesis, we get so QED, we're done. Quad erat demonstratum. We showed that this property holds that the empty list is a right identity for plus. Now, I'm going to do one more. This one is a helpful lemma in the homework. I apologize for the homework. There's one problem that probably this will be very helpful. And we're going to first define, so we've got append. All right, now function last. Okay, so I'm gonna rewrite this down here. Copy, I'll say functions. Okay, so there's that. And then last of the singleton x is equal to x, and last of x constant to x's is equal to last of x's, and the last of empty is equal to bottom. and I don't have a good symbol for bottom. So I'll just write, I don't know. What am I going to write? Um, $sign. Burn up a lot of, um, you crash. So what we want to prove is that as a lemma that will help you in your, oh God, I guess it's this. I feel like I see a hair hanging off of me. There's the lemma that you're going to need in your homework is to show that that for all y's, I say, let's see, for all x of type A, and for all, um, let's say, y's of type A list, that last of y's plus the singleton x is just equal to x. Okay, so this is a theorem. You'll be able to use this on problem 3 or 4 to finish off your proof. I forget which one. We can look in a minute, but let's see. So proof. Choose an arbitrary x. And do induction on the list, the arbitrary, I'll say the list y's. So what is the property of y's? Well, I chose an arbitrary x, so I got rid of that. And so now I'm here, I've got one y, so here's my property of y's. P of y's is equal to y's plus x. Whoops, sorry. Y's plus x singleton x is equal to x. And this is last, sorry, last. Okay. Base case, P of empty is equal to last of empty plus x is equal to x. That's what we have to show. But by the definition, I'll say here, by definition, append last of that is equal to last of singleton x, and by definition of last of x is equal to x. So that ends the base case. So the induction step. So assume P of, let's say, y's, and show P of, P of y colon y's. So the induction hypothesis key of y's says that what? This. Copy, paste. Show last of y colon y's plus x singleton x is equal to x. It's equal to just plain old x. By definition of append, last of y colon y's plus x is equal to last of y colon y's plus x. And now, by definition of last, last of y constant to y's plus. Oh, this should be a last x. X is equal to by the definition of last, that's equal to the last of y's plus singleton x. And by our induction hypothesis, we get that last of y's plus singleton x is equal to x. And so that's the end of the proof. Okay. Well, I guess that's the end of that lecture.